Chapter 4 was called Moving Electrons, and it was where we got to look at electrons and the different types of electrons in an atom and the responsibility that they have in terms of chemistry. So we started off the chapter by doing an experiment called the flame test, where we got to see some cool colors in the Bunsen burner flame, and we came to the conclusion that the colors were formed, and really the colors were responsible for identifying the metal atoms that were in a substance. And each metal atom gave a characteristic color in the flame. Copper was probably the one that we remember the most. We should know that copper forms, if the compound contains copper, you get that sort of blue, really cool blue-green flame. We should know sodium gave us yellow, strontium gave us a deep red, and lithium gave us a red too. But they were different. Lithium and strontium were different reds. Lithium was more bright. Strontium was more deep brick red. And we use that to identify some substances. And we talked about the overall process that was causing the light in the first place. The idea that electrons, as they are untouched, exist in a ground state in the atom, where they're in the lowest energy level possible. And when we put those atoms in the Bunsen burner, they were provided some energy. So the electrons actually jump up to an excited state. And when the electrons fall back down into the ground state, which they will inevitably do because that's more stable for them, they will give off the energy they absorbed in the form of a photon, in the form of light. And that photon is going to be a different energy for each of the atoms, and that's why you get a different color. We used the spectroscope in the Bright Line lab, the Bright Line Spectra lab, where we looked at different tubes of elements, gases, hydrogen, helium, sodium, mercury, and we saw that each element gave a characteristic bright line for the similar reasons of the excited electrons falling back down to ground state to give us light. We were able to identify elements in a mixture by the bright line spectra. We call them fingerprints for elements. So it was another form of identification. Then we moved into looking at the simple atomic models and just looking at the difference between core electrons and valence electrons. The idea that valence electrons were the electrons on the outermost level or shell of an atom, and the elements in the same group on the periodic table, the same columns, have the same number of valence electrons. That was one observation that we came across. And core electrons were basically all the other electrons except the valence electrons. So everything underneath the valence shell of electrons. And we came to the conclusion that elements in the same period have the same number of core electrons and also the same number of shells or energy levels, as we can see here. We looked at how ions form. So we talked about, with the bright line and the flame test, how the electrons can move from level to level, but what if it was provided so much energy that the electrons actually came off, or if electrons were added to the atom? Neutral atoms, we said before, have equal numbers of protons and electrons. But if a neutral atom loses electrons, remember electrons are negative, so if they're losing negative charges, they are left as positive, and we call those positive ions cations. If the neutral atom gains electrons, which are negative particles, then they become negative ions we call anions. And I gave you two examples here. So here's a neutral sodium atom, which loses its one valence electron, and what remains is a sodium +1 ion, because now you still have 11 protons because it's sodium, but now you have 10 electrons, so you have one extra positive charge. For here, fluorine, which has 7 valence electrons, gains one more, and now you have 10 electrons total in the atom. Compare that to the 9 protons, you have one extra negative charge, so that's why this forms an F- ion, an anion. If we look at aluminum, aluminum has 13 protons. And And we'll just choose one random isotope of aluminum. We'll give it 14 neutrons to make it aluminum-27. That's what's in the nucleus. If we look at the number of electrons for aluminum, there's 13 of them. So 2 of them are going to be in the first shell. 1, 2, 3, 4, 5, 6, 7, 8 can go in the second shell. That's 10. And then there are 1, 2, 3 remaining on the valence shell. Now, we looked at the idea of how metals tend to lose their electrons and become positive ions, and nonmetals tend to gain. So aluminum would lose these 3 electrons and become an Al plus 3 ion because of that. Sulfur, which has 16 protons. Let's do an isotope. Let's do sulfur 32, right? So there's 1, 2 electrons there on the first. On the second, there's 1, 2, 3, 4, 5, 6, 7, 8. So that's 10. And then on the third shell, there's 11, 12, 13, 14, 15, 16. Sulfur is going to gain 2 electrons to have 8. Remember that 8 is great, that octet rule. They're either losing or gaining to have 8 on the valence shell. Sulfur will gain 2 electrons to do that, becoming an S-2 ion. And we came up with the trends in the periodic table, the idea that group 1 form +1 ions, group 2 form +2, group 3 form +3, group 13, excuse me. 13 is +3. Group 14 can form +4 or -4. And then 15 formed -3, 16 -2, 17 -1, and 18 0, because they're the noble gases. They don't react, so they don't form ions. But there were those clear trends in the ion charges. And the driving force was really to be like a noble gas, right? They want to mimic, we called it noble gas envy. And that's what the cartoon is saying here, that saying the neon atom is saying you're all just wannabes, because all of these guys want to gain or lose the number of electrons to be like the closest noble gas. Once we had ions, we saw how the positive and negative ions could combine with each other, because positive and negative charges attract, and that's when you would get an ionic compound, which is a compound formed from the attraction of positive cations and negative anions. It's almost always a metal cation and a non-metal anion. Some exceptions, but almost always that case. And then after looking at an introduction to ionic compounds, we ended the unit with naming ionic compounds. There were a couple of different types. We looked at binary ionic compounds. Binary means there's one metal cation and one non-metal anion. And we looked at writing the formula from the name and the name from the formula. To write the formula from the name, we should write the symbols of each ion, including the charge. We have to use the periodic table for that. And then follow the rule of zero charge. Figure out how many ions you need to balance the overall net charge to 0. So for lithium phosphide, I'll do my scratch work here. Lithium is +1. Phosphide comes for phosphorus is -3. To balance a 0 charge, you need 3 lithiums for every 1 phosphorus. Barium fluoride. Barium is +2. Fluorine is -1. Rule of zero charge, you need 2 fluorines for every barium. Magnesium nitride. Magnesium is +2. Nitrogen is -3. Rule of zero charge, you need 3 magnesiums for every nitrogen. Writing the name from the formula, we're going to name the first element, name the second element, and then change the ending to "ide." We want to watch out for anomalies, though, which are nitrogen and phosphorus, basically. We drop the ending for most of the elements and change it to "ide," except for nitrogen. We don't say nitrogen or nitrogide, and we don't say phosphoride. We change it to nitride and phosphide. So the first element here is calcium. Second one is bromine. Change the ending to bromide. Here we have sodium. We change sulfur to sulfide. And then here we have aluminum. and we change chlorine to chloride. For ionic compounds with polyatomic ions, here's a list of polyatomic ions I gave you. You also have a chart that you had in your note packet, and you've had on several periodic tables that you've been handed throughout the year. A polyatomic ion is a group of atoms that are bonded together, that travel together, and that have a charge as a whole. So, for example, carbonate is a carbon bonded to 3 oxygens, and this entire group of atoms together has a charge of -2. They travel together, and that charge stays on the entire thing. It doesn't belong to just one of the atoms on there. Writing the formula from the name is pretty much the same as what we were just doing before with binaries, but we need to just double check whether or not the name contains just an element or contains a polyatomic ion. And what I mean is, like here, calcium nitrate, we want to compare that to something like magnesium nitride. Nitride just means nitrogen from the periodic table, but nitrate and nitrite are polyatomic ions. So double check the polyatomic ion chart first to make sure you have the right ion. Calcium is +2. Nitrate is NO3, all with a charge of -1. Rule of 0 charge. You need 2 nitrates. If you need more than one of the polyatomic ion, you're going to use parentheses. Throw parentheses around it. Aluminum is +3. Sulfate is SO4, all with a charge of -2. So it's Al2SO4 3. Strontium is +2. Hydroxide is -1. You need 2 hydroxides. That's strontium hydroxide. Writing the name from the formula, you're going to name the first element, and then you're going to name the polyatomic ion. Beryllium phosphate. Sodium, NO3 is nitrate. Ga is gallium. That polyatomic ion is acetate. The last type of ionic compound that we looked at were ionic compounds that contain a transition metal cation. Transition metals can be multiple charges for the most part. That's why there is no trend when we were looking at ion charges. So the consequence of that is when we have a transition metal that can be multiple charges, and I'm writing the name of the compound, we need to include a Roman numeral that tells me what the charge is. In the other examples, if we had sodium chloride, there's no need to tell me sodium is +1 because that's the only charge that sodium can be. We know that. We memorize that. Manganese, on the other hand, can be +2, +3, +4, +5, +7. So we need to include a Roman numeral with what the charge is. Here they're telling me it's manganese 2 chloride. Not how many manganese there are, but they're telling me that manganese has a charge of +2. Chlorine, as always, has a charge of -1. Rule of 0 charge. Manganese 2 chloride. Iron 3. Oxide. Oxygen is -2. That's Fe2O3. And then lead 2. Nitrate. Polyatomic ion. You need 2 nitrates from that. That's lead 2 nitrate. Writing the name is a little more difficult because we have to do a little bit of work. We have to sort of go backwards and look at what the metal is bonded to figure out what the charge is, because I have to include the Roman numeral in the name. So I pull the compound apart. I have tin sulfide. I know each sulfur is -2. If each sulfur is -2, this tin must be +4. So the correct name for this is tin 4 to tell me or to tell someone, whoever's reading it, the charge. Tin 4 sulfide. Cadmium something phosphide. I know each phosphorus is -3. That's -6 total. Each of these cadmiums then must be +2 to balance out. So that would be cadmium 2 phosphide. And then nickel 3 of them. 2 phosphates. Each phosphate is -3. Like -6, so each nickel must be +2 to balance out to 0. So nickel 2 phosphate. Now, one thing to remember, or several things to remember. Silver's in the transition metal group, which is group 3 through 12 here. But silver can only ever be one charge. It's always +1. So you have to remember that it doesn't get a Roman numeral because it can only be +1. Zinc and cadmium, which are also in the transition metal group, can only ever be +2. So they also don't get a Roman numeral in their name because zinc is only ever +2 and cadmium is only ever +2 as an ion. Lead and tin are outside of the transition metal group, right down here. But they can be multiple charges, so they get Roman numerals as well. So those are just some exceptions to keep an eye out for. We ended the chapter with doing a lab where we made paint, and we used cobalt and we used copper, because transition metal compounds are often colored because of the multiple charges that they can be. And one of the places where you should be familiar with where you would find transition metals are in paints and other colored pigments. So that took us to the end of chapter 4, which was moving electrons, where we looked at electron behavior, valence electrons versus core electrons, ion formation, cation, anion, noble gas, NV, and naming and writing formula for ionic compounds.